Hi there and welcome to this video for Senior Physics on Astrophysics. In this video we're going to look at circular motion and how it's affected in space. Alright, so we know that there are two main types of motion that an object can have in space. The Greeks first put forward the notion of circular motion. They loved the idea of circles, and basically we're looking at things like moons and artificial satellites that will deal with that circular motion. Kepler put forward the idea of elliptical motion, which basically is the movement of planets around the Sun, and in some cases that might have some artificial satellites. So we get a scenario that looks like this for the elliptical motion. For the circular motion, we'll get something that looks like this. Here we've got a moon going around the Earth, and it's again in a circular motion. Our satellites will do exactly the same thing, such as our communication satellites, our weather satellites, our TV, you name it. Then we've also got the idea that on the Earth, points on the Earth's surface also will have a circular path. So if you take any point on the Earth, like Australia, if we look at it on the Earth and we follow its motion, it's going to be going in a circle. Well, that's really important if we want to put a geostationary satellite up in space. So a geostationary satellite basically is a satellite which is going to sit over the same place at the same time. So we've got this idea of circles. So in order to understand how circles work, what we've got to do is to go back and look at our circular motion unit. So our circular motion unit allowed us to use a variety of different formulae, and they stemmed from Newton's first law, which basically is his law of inertia, that basically stated that an object will move in a straight line unless a force is applied upon it. If a force is applied upon it, then the velocity will change over time, and as a result that mass will accelerate. Hence we get F equals ma. And finally his third law was the fact that we've got action and reaction. Now what we notice that if we apply a force on a moving object which is at 90 degrees in the motion and continue it, then what will happen is that object will move in a circular motion, and we call this centripetal motion. So you can see here that we've got an object shown with the orange blob which is moving at a velocity v1. If we apply a force Fc, which is the yellow arrow, perpendicular to its motion, the result is it will move in a direction, stay at a constant speed, but move in a direction v2. So as a result, we've now produced our circular motion. Now we know that centripetal acceleration, the rate at which it changes its speed, can be calculated by v squared over the radius of r, which is the radius of the circle. Then we can apply this into Newton's second law, which is F equals ma. So instead of A, we will put AC, which is the acceleration due to centripetal force, and the result is we can work out the centripetal force using mv squared over r, where v squared over r was the centripetal acceleration. So these are our two major formulas which we can utilise. But it doesn't just stop there. We also know about revolutions per second. So let's look at revolutions per second with respect to applying them into our centripetal force and centripetal acceleration models. Now we know that in order to work out the circumference of a circle, we've got 2 pi r. We also know that we've got a time period. Now the time period is the time for an object to make one complete revolution, or do 2 pi r of the circle. So we can now substitute that into velocity. We know that velocity is distance over time. So in this case, the distance is going to be our circular distance, which is 2 pi r, and the time is going to be the time period, the time to actually travel one complete circle. So instead of distance over time, what we then end up with is 2 pi r over t. Now we also know that we've got centripetal acceleration, which is v squared over r. So now we can substitute into v 2 pi r over t squared, and that will all be placed over r. So as a result, rearranging, we get AC equals 4 pi squared over r squared divided by rt squared. Now our 2 r's are going to cancel. So as a result, our centripetal acceleration in circular orbit basically is given by 4 pi squared r divided by t squared. Now we can now substitute all of that into our formula for centripetal force. We know that centripetal force is mv squared over r. but we can now substitute in for AC. AC obviously is going to be V squared over R, so as a result we get the centripetal force will be M, that's our mass, and then 4 pi squared over R divided by T squared. Note that that is our V squared over R equation from the green squares that you can see above. So those are a variety of different formulae that we can utilize using our circular motion, and then this can be applied into space. So let's have a look at an example. Here we've got the radius of the Earth at the equator is 6.4 times 10 to the 6 meters, and its mass is 6 times 10 to the 24 kilograms. We're going to calculate the centripetal acceleration of a point at the equator, the centripetal force acting on this point, and the linear velocity of this point. So, the centripetal acceleration, firstly we need to know that the time period to travel is 24 hours, which is 86,400 seconds. So I can now substitute that into my formula, 4 pi squared R over T squared, and as a result I can get 0.034 meters per second for my centripetal acceleration. I can now add this to my mv squared over R formula to find the centripetal force at this point. Now really all I have to do is multiply this by its mass. However, we're going to do this underneath, so its mass is 6 times 10 to the 24 times 0.034 times 2 equals 2.04 times 10 to the 23 newtons. So I've now found my centripetal acceleration. I've also found my centripetal force. Now I want to find my linear velocity. Well, we know that velocity equals 2 pi r over t. I know what my I know what my radius is. It's 6.4 times 10. That should be to the 6 to the power of 6, divided by the time in seconds, which is 86,400 seconds. So at this point, at a specific point on the radius of the Earth on the equator, I would be travelling at 465 meters per second. Okay, so I hope that makes sense and shows you an idea as to how we can look at revolutions per second and manipulate that into our centripetal force and acceleration equations. Okay, so what I'm going to do is put a few more exercises up on this post in this course, and hopefully you'll be able to download them and work your way through them. Well, I hope you found that useful, and I look forward to you joining me again. Bye for now.